Hey guys, hello everyone. Welcome to Rasayan Academy once again. Now we are going to move onwards to study group 14. But before that, I told you I will be discussing few questions on group 13 which have been asked in the recent CSIR NET papers. Okay, these are some really important questions. So let's check them out. First of all, this question is taken from 2020-22 February examination. So which of the statements from A to D, there are four statements given below, are correct for B2H6 molecule? Alright, so read out the four statements. Out of this, which one is going to be correct? Okay, you have to do this by yourself, then I'm going to discuss the answer. Right, so addition of etherate complex of BF3 to NaBH4 in a polyether solvent produces B2H6. Is this true? Yes or no? See guys, that's why studying in, reactions is important. So I have told you previously, where did that reaction go? See, this one, 5 number reaction for the formation of diborane. So BF3 plus NaBH4, that is going to give you NaBF4 plus B2H6. So definitely when you are taking a etherate complex, why we are not taking aqueous solvent? Because then water will be reacting. That's why we are taking a neutral ether solvent over here. Okay, so that makes a very good question. ये direct question आ गया, isn't it? Let's get back to our question now. Yes. So yes, this is true. We are going to get diborane if we are reacting BF3 and NaBH4. We have just seen the reaction that we have studied. Now, B2H6 molecule, it has D2D symmetry. So you have to find this out by drawing the structure. And you must know this is the structure of diborane. So basically, see, this boron looks like it has become tetrahedral. That means two of the hydrogens are going to be on this plane. It is on one plane, and these two hydrogens are on a plane which is perpendicular to the plane of paper. So that means all of the molecule is not planar. But how do we find out the symmetry? We have to see what are the symmetry elements first of all. So there is a C2 axis passing through the molecule like this, one C2. So when do we get the D term? We get the D term when we have one C2 plus two C2 again. That gives you the D2. After that, if we see how do we get the other two C2s? It is very easy. You can get from here as well as from here. Okay, this molecule is just going to look like allene. I have already discussed that in organic stereochemistry. Okay, so just check that out as well. Now, this is how you do the D2 symmetry. Fine. After that, do I see a plane of symmetry that is, bisecting the principal axis? This is our principal C2 axis. Why? Because it passes through both the boron atoms. And I have a sigma plane which is bisecting, or it is perpendicular to the principal axis. That is my sigma H plane. So the point group is D2H and not D2D. So B2H6 is going to be D2H symmetry. Alright, so this is wrong. A was correct, B is wrong. Reaction of B2H6 with ammonia, this is an amine. That gives you Me3N.BH3. See, I told you this has been asked repeatedly in many different ways. Okay, so यहाँ पे एक option बना दिया, otherwise it could have been a direct question also. So yeah, it is also correct. B2H6 breaks down symmetrically when I'm taking heavier amines like this. Okay, I've also discussed. So this is correct. It is diamagnetic in nature. So you know that boron is electron deficient, and when it is present in simple BH3, it has all the three electrons bound with these hydrogens. So no electron is left out, but still it has a vacant p orbital. So that vacant p orbital is sharing electrons with the hydrogen boron bond of the other borane like this. So there is no unpaired electron in the molecule. So it is diamagnetic, true. A, C and D. A, C and D are correct. So 2 is the correct answer. I hope that you have also got it correct. Next question, again, this is from June 2024, and this question is taken directly from the back questions of Shriver and Atkins. Okay, so in the following reaction, A, B, and C respectively are. A, B, and C you have to find out. Try this by yourself, and I will definitely answer. This is Li. So what happens when BF3 is reacting with any reducing agent? It is definitely going to give you diborane. Right, definitely this is going to give you that. Other than that, you will have lithium fluoride, aluminium fluoride, right? Simple. So A is going to be diborane. But if you are putting water to diborane, it is going to hydrolyze to give you orthoboric acid. You write it like this or you write it like this. This is going to be B. When you heat the orthoboric acid, what do you get? If there's a metal or an alkali, you get the metaborates. But if you're directly heating, you will just simply get the boron oxide, trioxide. So this is going to be C. So what do you get? You get, first of all, it's not written B2H6, but it's okay. If BH3 is written, that is also fine because these two are just dimers. So BH3, then your orthoboric acid in option number B, and lastly you're getting B2O3. So this is going to be your correct answer. Alright, you are not getting LiBH4. No, the substitution gives you diborane. Next, 5 moles of B9H14 minus reacts with 2 moles of B5H9 at 85 degrees centigrade, resulting in the evolution of 9 moles of hydrogen and the formation of a monoanionic borane cluster that has a dash structure. Okay, question asked in June 2023. Interesting question, guys. See, there are some reactions which are all over the book, all over the internet, but we usually don't pay attention to them. This is one of those reactions, right? So 5 moles, it is very clearly mentioned, 5 moles B9H14 minus. Acha, minus hai? So let's just consider that I'm taking the potassium salt because I want to balance. So I'm taking 5 moles of this, reacts with 2 moles, it's a neutral compound B5H9. Now what is to be done? What can be done? Already it is mentioned 9 moles of hydrogen. So you are just trying to find out which borane has formed. So हम क्या करेंगे? This is very simple. Just add everything. 5 into 9 is 45. So 45 boron from this side plus 5 into 2, 10 boron from this side. Total कितना हो? 55 boron. Isn't it? Yes. Add the hydrogens now. See, you are having, okay, be more careful about this because monoanionic, the product is also monoanionic. That means you can add a K over here. Okay, now 55 boron in total. How many hydrogens are present? You are having 9 into 2, 18 hydrogens in the product side, and in the reactant side, you have 18 only over here. Yahi pe 18 aa gaya. On this side, you have how many hydrogen? You have 5K, 70 hydrogens. Okay, so 5K, I have to take the 5K in consideration, and I have 70 hydrogens and 55 boron. How is that possible? In दोनों में से 5 common निकाल दो. Just eliminate 5 from this. Let's write it over here. 55 boron plus 70 hydrogen. Just eliminate 5 common from this one because we have to put a 5 over here. Alright. That means 11 boron plus 14 hydrogen. Right? The formula becomes B11H14. And since there is 5 potassium present, that is monoanionic. So B11H14. It was very easy. I'm just doing maths. There is no chemistry in this. Okay. Now, once again, just check all of this because you have to balance the whole equation. Okay. You have to be kind of balancing this whole equation. 5, 2. This was already given. This was also already given. You just found out this 5K B11H14. Chalo. So what is the structure of this one? B11H14 minus. This minus you can take up just for calculation. You can take up like this. So this is BNHN plus 4. This is a nido structure. HN plus 2 is closo, HN plus 4 is nido. Alright, so this is a nido structure. So this is your answer, nido. Chalo, let's move onwards. Next easy question. For the following reaction sequence, 3NH4Cl plus BCl3 gives you X in the first step, then hydrolysis gives you Y. Again, try this. Alright, you have done this yesterday only. If you have seen the video properly till the end, you will know that what reaction is taking place in between ammonium chloride and BCl3. Nitrogen will get connected to H, boron stays connected to Cl. You are getting BBB trichloroborazine like this. This is what you get. Okay, in the first step. In the first step, you are getting this trichloro. In the next step, LiBH4 reduction is taking place. So this is the first step. The next step you are going to get BN, BN, BN. Alright, complete reduction. LiBH4 is taken for complete reduction. So now you are having the borazine, the second step. So this is what X is like. It's written in a different manner, okay? Doesn't matter. It is BH, NH separately written whole thrice. So our answer is either A or B. C and D seems to be very strange because ammonium does not exist anymore. No separate ammonium now. Yes, now after I am putting water, 3 moles of water. Remember the situation? 3 moles like partial hydrolysis, 9 moles complete hydrolysis. So 3 moles I am only going to put OH onto boron. So what am I going to do? I cannot write it like a benzene. Right. So even though it's easier to write. Alright, so I'm adding the OH on boron. This is a addition reaction, isn't it? Yes, 2 hydrogens on nitrogen. Then 1 OH like this. HOH. Alright, I did on the nitrogen, yeah. 2 hydrogens over here again. So this is how it is going to be. And just eliminate the double bonds now because everything will be pentavalent. Yes. This is how the molecule is going to be. So the answer is going to be B, OH, H and NH2 whole thrice. So first one is the correct answer. We have done it already. Let's see in our previous, see, we got how many? For 9H2O, we got complete hydrolysis. For 3H2O, we actually got substitution. So is there substitution possible in the product side? Let's see. In the options, what is given? Yeah, in the options, what is given? Nitrogen, NH2OH is given and B is H. So this is absolutely wrong. Yes, not possible. So here we are giving the addition product, BH and OH. This is the only possible answer because all the other options are wrong. Okay, chalo. This is a very, very important question asked in June 2024. Very interesting question. In the following reaction, A and B respectively are. Ye dekho. In this following reaction, you have taken gallium trichloride, 4Me3SiH, silane gives you A, again reduction gives you B. It is a very interesting question, guys, and something new. Okay, so what is happening? Can you answer this by yourself? Yes, try it out first. Then we are going to do the answer. All right. So what is happening in the presence of trimethylsilane? What is this molecule going to do? It is replacing the chlorines from the gallium compound and it is giving you hydrogen and it is taking away the Cl. You know that silicon has a very high affinity for electronegative groups like oxygen, fluorine, silicon like that. So your final product is going to be a digalene, and the structure is very similar to a diborane, isn't it? Two of these are going to be perpendicular, just like that. Diborane, just like diborane, we have a digalene. Interesting. So, yes, Ga2Cl6 plus Me3SiH, what is going to happen? First of all, it's going to give you an intermediate. This intermediate actually looks like this. Two hydrogens on the gallium and one Cl each. One Cl for each gallium, like this. So this is going to be an intermediate first of all. Now, once again, it is going to react with lithium GaH4, which is formed, yeah, by the reaction of GaCl3 and LiAlH4, and this is going to finally give you the digalene plus 2Cl. So this is how the reaction is going to be. Yes. All right, guys. Interesting thing to happen. So just star mark this one. Very interesting new question. So what is going to be the final answer? You first of all, you're going to have this 2Cl bridging, and finally your digalene. This is correct. Option number 1. What about these two? No, you cannot have Cl on the side and hydrogen bridging. No, when Cl is present, it is more electron rich. It has lone pair, so hydrogen cannot be bridging in the presence of chlorine. Not possible. And 3 chlorines, no. Again, the structures are wrong. This is correct, but this is wrong. Right? First one is the correct answer. Chalo, you always have to check all the other options. Just go and directly go with the right one. Right. Chalo, now we are going to start group 14. Alright guys, so I hope that now since we are doing questions together, you are liking main group elements, which is usually considered to be a boring topic. Nobody wants to study this, but yeah, it helps you score a lot of marks because there are some direct questions every time. Right, so yeah, let's move onwards. Now, there's one more important thing I want to tell you. Whenever you study main group elements, the questions are not necessarily going to be on one single group. Okay, they can be on one single molecule, like just we saw, like the question was on B2H6. Sometimes the questions are like this, which is giving you a mixture of group 14, 15, 16, 17, like 4, 5 at once. Sometimes it's very specific, sometimes it's very general. Okay, so just look at this thing in that point of view. You have to study this generally, like overall idea you should have about the main group elements and the periodic table. And for those questions, and just whenever you solve the previous year question, you will get the idea that which molecule or what area is being always focused on. So only that portion we are going to be very specific about. Okay, so I just wanted to inform you about that. Now let's move onwards and study about the carbon family, group 14 elements. Okay, so first thing guys, let's see the electronic configuration. Very simple. Group 14 has NS2 NP2 electronic configuration. All right. So for carbon it is 2s2 2p2, silicon 3s2 3p2, germanium 3d10 4s2 4p2. Now see, from germanium the d orbital is introduced, so you know what can happen. What is going to be the effect on ionization energy as well as the radius. Okay. Then we have tin. Tin is okay. D and then S and P. Lead, you have 4F14, then 5D, then S and P. So definitely there is going to be an inert pair effect for the 6s2. Just by looking at the electronic configuration, you can very clearly see. And also the ionization energy is going to be a little bit higher than the tin. Also the size. Chalo, let's see. Now, atomic radii of group 14 elements are smaller than group 13 elements because left to right moving, your nuclear charge increases and the size decreases naturally. Okay. The first ionization enthalpy goes like this. Carbon is smallest, and that's why maximum ionization enthalpy. Moving on to silicon, okay, good, which is greater than germanium. Now it should have been like germanium should have just like gallium and aluminium. Gallium also had only 1 kilojoule per mole greater than aluminium. So that was not a huge difference. And when you move onwards to group 15, it will increase, the ionization energy will decrease gradually. Nothing happens because of introduction of D and F orbital. So this group 14 is in between 13 and 15. So it shows like middle properties. So silicon still has more ionization enthalpy than germanium. Then we go to tin, which is okay, but tin has lesser than lead because lead में कुछ ज़्यादा ही effect हो गया है because both the F and the D orbital added. Both F and D orbital added, that's why increased effect. Okay. So here you only have to remember the exception of lead. Okay. And all of this is just decreasing down the group. This is because of the poor shielding effect of d orbitals and f orbitals in lead. So, okay, you have a general idea. As we go down the group, the ionic character increases and covalent character is predominant for carbon and silicon. Why is that so? Because when you move down the group, the metallic property increases. So, tin and lead are metals only. Germanium is also like metal, but silicon is a non-metal and carbon is complete non-metal. Germanium is like a metalloid. Okay, it shows both the properties of metal and non-metal. So tin is amphoteric while lead is a complete metal. So tin is like aluminium. It's mostly a metal, but it can react with bases also. And it can still form covalent compounds like SnCl4, SnCl2, right? So oxidation state of this group are +2 and +4, and the stability of +4 decreases down the group. Why? Because of inert pair effect, and hence PbO2 and lead tetraacetate, which has lead in +4 oxidation state, both of them, they are highly oxidizing in nature. Lead tetraacetate is used as a reagent in organic chemistry, and same goes for PbO2. Both of them have lead in +4 oxidation state. +4 means you are removing this and these, all of these electrons. But because of the inert pair effect, of lead of the 6s2 orbital, it does not want to go to +4. So it will be very readily going to +2 again. Alright, so these were just some general points. Now let's also discuss the first ionization energy. What happens for carbon smallest and it's a non-metal, so maximum, and it decreases for silicon, decreases further for germanium, decreases for tin. Tin से थोड़ा सा ज़्यादा है lead का, just slightly bigger for lead. Okay, only slightly bigger, right? Atomic radius, ionic radius, you can see it increases normally, normal increase. Melting point and boiling point again is just understanding of the packing. Graphite, diamond, carbon has many allotropes and we are going to talk about those. So definitely it is going to be very hard. Then comes silicon, germanium, tin and lead. See, lead now becomes a metal. So metal has a better packing. That's why it is going to be stronger than tin. Okay. So just normal things. So guys, there is a lot to talk about while we are talking about the whole group. There is allotropy, there is formation of some specific compounds or specific allotropes, and the silicates, many important things to talk about. Okay, chalo. So first of all, allotropy of carbon. We are talking about carbon. Now, all the elements except lead show allotropy. Carbon shows allotropy, and silicon shows a little bit of allotropy like silica, SiO2, which is sand, and SiO2 is also quartz. You already know that. And germanium, we have gray germanium, and the tin, white and gray. So like only few allotropes for the lower elements, more for carbon. Carbon exists in sp3 hybridization in adamantane, which is the monomer unit of diamond. Here it is sp3 hybridized, and that is why the structure is like very strong. Okay, it's a complete covalent solid. What is a covalent solid? Covalent solid is one which is completely formed out of covalent bonds, and it is the strongest in the whole world, right? Graphite has sp2 carbon linked to each other by three covalent bonds, forming sheets which are held together by van der Waals forces of attraction. So you see that these are all sheets where the carbon is sp2 hybridized, and it has a p orbital like this. It has all of these have 1 p orbital where they are going to be 1 electrons. So those free electrons are going to move around, isn't it? All those 1 electrons are going to move around the whole of the graphite structure, making it a good electricity conductor. So diamond is a good conductor of heat because these particles, just these carbon atoms, they can just vibrate on their own position. They cannot move around. While graphite is a good conductor of electricity because of the sp2 hybridization and plus 1 p electron. All right, let's move onwards. And yes, guys, I told you I'll be showing you the difference, the exact difference between boron nitride and graphite. So see, this is the difference I wanted to show you, this thing, the structural difference mostly. Why? Because here in the graphite, all of the elements are all carbon only, right? So carbon does not want to superimpose carbon. That's why the sheet are like not exactly superimposing. They are like in successive layers are basically offset. Yes, they are offset, not exactly onto the carbon over here, like this. Now, in boron nitride, since it is alternative element, so they are exactly superimposing vertical layers. Okay, so that is the main difference in the structure. Now, boron nitride is a crystalline material made of boron and nitrogen atom linked by covalent bond. And graphite is also crystalline material. What is crystalline? Anything which has a proper structure is crystalline. Made of pure carbon atom arranged in hexagonal lattice with covalent bonds within each layer. Okay. Boron nitride is an insulator due to lack of free electrons, and you know graphite has free electrons, so it can delocalize those and be a good conductor. Boron nitride is highly inert, chemically inactive at very high temperature, and graphite can react with oxygen at high temperature, releasing carbon dioxide. So graphite can actually burn. White or grayish white in color, black or grayish black in color. All right, so these are the differences between boron nitride and graphite. Now let's move onwards to another allotrope of carbon, that is fullerenes. So fullerenes have been very popular recently, not only because of the structure but also because of the chemistry. So let's talk about all of it. So fullerenes are produced by graphite sublimation. The soot is dissolved in benzene and separated chromatographically to give you C60, C70, C76, etc. So basically when you are subliming, what is sublimation, guys? I think everyone knows, that is direct from solid to gas. Okay, when you are heating graphite in some particular condition, it sublimes directly going from the solid phase to gas, no liquid. So the soot, what is the soot? The black material, like which you get after burning. That soot is collected, dissolved in benzene, and when it is separated chromatographically. Why chromatographically? Because these balls will have different properties of adsorption. That's why they can be separated to give you different size of these balls, and specifically the C60 soccer ball is known as the Buckminster fullerene. तो सिर्फ C60 का नाम ही fullerene है, all of these are not fullerene, only C60 is fullerene. Okay, now one more important thing. So now if the questioner is like particularly asking you about how many 5-membered and 6-membered rings which are present in fullerene, fullerene is C60, okay, and in C60 you have 12 pentagons and 20 hexagons, all right, and the total number of faces, let's say it's asking you number of faces, so 32 number of total faces are present, okay, on a Buckminster fullerene. And if they're asking you individually, 12 pentagon, 20 hexagon. Just remember that. Alright, so now guys, we are going to move onwards and talk about graphite, graphene, all of that. So, ये देखो एक important चीज है. I just saw this in Shriver and Atkins and I thought this has to be told. Potassium graphite compounds shows two type of alteration of intercalated atoms. What is intercalated atoms? Intercalated atoms means the atoms which get into the lattice of a particular big molecule. Like now graphite is a big molecule because all of it is like looking like one molecule only, everything is interconnected. When I have introduction of potassium, it forms various intercalated atoms. Matlab the stoichiometry won't be same. Sometimes it is Kc8, that is 8 atoms surrounding one potassium like this. Sometimes 36 atoms surrounding one potassium. So the stoichiometry keeps on changing. Okay. Yes, but potassium can form intercalated compounds. It has been asked in your exam already. So yeah, just remember this. It's not something random I'm telling you. Okay, chalo, ye kya hai guys? Yes. See, fullerenes can be reduced to form 60 fulleride salts. That is C60N. Now N could be 1 to 12. Now, fullerenes of alkali metals are solids having compositions such as K3C60. So, potassium takes a lot of interest in graphite as well as fullerene. The structure of K3C60 consists of a face-centered cubic array of C60. So, guys, till now this has not been asked, but I hope that in the future, if this is asked, you will be able to tell. What is the type of lattice? C60 face centered. Okay, it is FCC lattice according to the C60. So C60 balls are arranged in FCC lattice. Okay, which is the most efficient lattice. Okay, in which potassium ions occupy the one octahedral and two tetrahedral side available to each C63 minus ion. So according to 1C60, potassium occupies one octahedral and two tetrahedral side with respect to each 60. That's why it is like K3C60 like that. Okay, yeah. The compound is metallic conductor at room temperature and a superconductor below 18 K. So, when you are studying a strange compound, you should know why you are studying this. So, these are some of the properties. It is a metallic conductor at room temperature and a superconductor below 18 K. That's why maybe it is very important. Other superconducting salts include Rb2CsC60. So other salts are also made, which has a superconducting transition temperature of 33 K and CS3C60 with critical temperature of 40 K. So these are very low temperatures. 33 K is like very low. 273 K is your 0 degrees. से बहुत ज़्यादा low है. Okay. The conductivity of E3 C60 compound can be explained by considering the conduction electrons are donated to the C60 molecule and are mobile because of overlapping C60 molecular orbitals. So we don't want to go very deep into the molecular orbital stuff, but just remember that these compounds of fullerene are behaving as superconductor at very low temperature. And what are the examples of these? K3C60. Then you have rubidium 2 cesium C60. Then you also have C60E3 like this. Okay. So just remember this. It's a FCC lattice. Moving onwards to another important thing. ये भी आ चुका है already in the examination where the fullerene is actually behaving as an alkene donor, right? Fullerene metal complexes, this has also been identified. The polyhedral fullerenes undergo reversible multi-electron reduction and form complexes with D-metal organometallic compound and with osmium tetraoxide. So guys, we are not just studying some simple main group elements, the trends. We are not just studying the trends. We are also studying what is going on with the allotropes of carbon, like something advanced. So you have to like pressure your mind a little bit more. Okay. So look over here. This is just like a simple compound, like an alkene donating to platinum. Nothing huge, right? It would have formed a complex like this. So instead of this double bond, you just have this double bond. Definitely there is a double bond over here. Now, what if you don't write the double bond? If you have studied organometallics with me, you know that what kind of a model is this? This is a metallacyclopropane structure, right? So if you study organometallics, you will know what kind of a triangle bond is this. It is just a double bond only, but with a lot of pi back bonding, right? So this is one example of fullerene metal complex P diphosphine C60, right? And this is how the C2 p pi orbitals are present. All right, chalo. Next, three examples we are taking. First one this, second one with a ruthenium complex. Now it is doing the same thing. You know, it's these triangle bonds that you can see, you can simply write them as like this. Carbonyl, 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 no problem. This is just an alkene. Just one double bond with this alkene. This ruthenium again, because ruthenium are present in triangles. Ruthenium are present in triangles like this. CO, 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 one more CO, and then again a double bond. This ruthenium will again form a double bond. All right, and this ruthenium over here is again like this, CO, CO, CO. So this is nothing huge, guys. Instead of a carbonyl, you are just replacing the carbonyl with a double bond, and that double bond you're writing as a metallacycle. Okay, just like this, just like this. Okay, all of these are forming these triangles. Very simple, nothing huge. See, with three different double bonds of a hexagon. Why a hexagon? Because right, hexagon is going to have three bonds just like benzene. So let's say if I want to draw, it's how is it going to look like? This double bond, then let's say the alternative double bond, then let's say the alternative double bond like this. Isn't it? Just like a simple benzene. Okay, like this one over here. The same thing happens with osmium, but here osmium tetraoxide has to be provided pyridine so that it becomes a little bit electron rich, and only these one double bond is forming a 5-membered ring with osmium and oxygen. This type of bonding is different. This is just alkene to metal. This is also just alkene to metal. However, this is carbon oxygen proper bond. Okay, so these are three different types of examples that I have discussed. Okay, I think that you find it interesting. You won't be able to like draw, so just download the PDF. Okay, now let's move onwards to the third one, that is graphene. So I hope that you have a little idea about what is graphene. So we're just going to like see the uses and the structure of graphene. That's it. So you have seen graphite. What is graphite? Many layers of sp2 hybridized carbon forming sheets. So graphite consists of multiple layers of carbon atom. A single isolated layer is graphene. That is, अभी ये जो graphite था, we have discussed graphite over here. This one, this complete thing is graphite, many different sheets lined on the top of each other. If I just separate out one long sheet, एक लंबी sheet को separate कर लिया, that one thin, very thin single sheet of carbon 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 in just one linear manner, that is graphene. Okay, graphene is remarkably resistant to fracture and deformation. मतलब you might think कि it's a very thin layer, it might be very weak, but no, it is resistant to fracture. That also very resistant to, मतलब it is very strong and flexible. Okay, It has a high thermal conductivity. That is what makes graphene so interesting, and has a conduction band that touches its valence band. So conduction band touching the valence band means highly conducting. Okay, adding functional group influences the electrical properties of graphene. Some might enhance, like more electron donating groups can enhance, electron withdrawing groups are going to deteriorate the electrical conductivity. That is very obvious. Graphene has been prepared both by mechanically peeling away layers of graphite, mechanically removing layers of graphite. I don't know how that is done, and by chemical vapor deposition on metal substrates. The chemical reduction of graphite oxide, um, and sonication of colloidal suspension of graphite oxide. So these are just different methods by which graphene is being made. The more important thing is to know the properties of graphene. So what are the applications of graphene? Numerous applications of graphene have been still proposed, including their use in energy storage materials, microsensing devices, liquid crystal display, polymer composites, and electronic devices. These kind of technologies make our phones so slim. Okay, so yes, graphene this is how it looks. Just one single layer plugged out of graphite. Just understand it like this. All right, guys, I think that you are finding all of these things interesting. We are going to move onwards and see more allotropes and more reactions. All right. All right, guys. So now we are going to move onwards and understand some small important factors. See, guys, there is a whole lot of organic chemistry, a different subject based on the carbon properties. So we are mostly going to focus on the allotropes, the general properties of carbon here, and then we move onwards to the properties of silicon. So we are going to see what kind of bonding they do, and directly jump onto the silicates and the silicones. Okay, those are some important things we discuss in group 14 here. Now, due to small size and high electronegativity, carbon forms the p-pi bonds with itself in alkene and alkyne. This we have discussed in chemical bonding as well, and periodicity also. However, it isn't possible for bigger atoms like silicon and germanium to do so. So they are very poor in simple p-pi bonding. However, they sometimes give you the p-pi-d-pi bonds like in NSiH3 whole 3. So you have a proof of that when you are taking NCH3 whole 3 trimethylamine. When you are taking this, definitely the molecule is pyramidal. But when you are taking the same trisilyl amine like this, it is planar. It is planar in nature. Why is that so? Because here you need a p orbital to interact with the d orbital. See, you need a p orbital to interact with the d orbitals of silicon, which gives you the pi bonding, just like this one. Okay, p pi d pi bonding. So this is a proof that bigger elements are present, they prefer to give you p-pi d-pi bonds rather than simple p-pi bond. Now, other elements due to very big size don't participate in pi bonds. Other elements of the same group like tin and lead, they don't do that. Carbon, just like silicon and germanium, does not have the possibility of complex formation due to absence of vacant d orbitals. So it can form catenation by formation of many sigma bonds. It can form many pi bonds, but it cannot directly do a complex formation like silicon. Okay. However, there are many ligands which the carbon can have, like carbonyl, like the ethene, many different things. And guys, we are not going to talk about carbon monoxide or dioxide over here, because we have a different organometallic chapter on metal carbonyls. Okay, so I think that is good enough. Also, when you want to see all of these in high oxidation states, these are few of those compounds. SiF 5 minus, silicon is there in +4. SiF 6 2 minus, again +4. Germanium 6 2 minus, all of these are present in +4. Okay. All right. So now we are directly going to jump on to the compound of silicon with oxygen. So you have silica, then you have quartz. Those are two allotropes of the same silicon-oxygen bond. But the SiO-Si link is not just present as silica in earth, also present as wide range of silicate minerals and silicone polymers. Silicone polymers are synthesized. So we will discuss that later on. First, let's talk about silicate minerals. Okay, so I've taken like all of those silicate minerals in one slide only. So you just have to be, looking carefully. So what is orthosilicate? Orthosilicate means only just one unit of the silicate. One unit is SiO4 4 minus. How does it look like? It is tetrahedral in nature. O minus, O minus, O minus and O minus. What is this? Just one tetrahedral unit. Nothing else. Alright. So only orthosilicates are those only having one unit. For example, phenacite Be2SiO4, willemite Zn2SiO4. So I've given you two examples of orthosilicate. If you remember that, it will be good enough. Okay, remembering the silicates is difficult, so remembering only two examples will be good enough. Now, when you are having two of the SiO4 units connected to each other, they are going to look like islands. Okay, let me show you. They're known as pyrosilicate. Pyroborate bhi tha. Pyroborate means again two borate units that were two triangles, but here we are not having two triangles, we are having two island-like structures. So basically looks like triangle but have one oxygen in sharing. So this oxygen is in sharing. There is one silicon, one O minus, another O minus. This is not O minus. This is simply an oxygen. This is silicon, O minus, O minus, and one oxygen is on the top of that silicon like this. So it is going to be O minus over here and O minus over here. Looks like islands. Okay, इसको island structure भी बोलते हैं. Island structure. Okay. For example, the formula, since there is one oxygen common now, there are two silicons, Si2. How many oxygens are there? 1, 2, 3, 4, 5, 6, 7. 7 oxygens, how many of them are minus? Except one, all are minus. So 6 minus. This is the structure of pyrosilicate. Example is scandium pyrosilicate like this. इसका नाम है thortwitite. Thortwitite is the name, common name of the scandium pyrosilicate. ठीक है, example. Another one, the another type. When two oxygens of silicate unit are shared with one another, the ring is formed. See, if I'm having this one shared and this one also shared, then what will happen? I might form a three-membered ring like this, isn't it? So a three-membered ring is also possible, a six-membered ring is also possible, a four-membered, 12-membered, eight-membered, many. So you see, here I'm having a three-membered ring. That is three silicates. These are the oxygens which are common. Okay, and these are the ones which are on the top of silicon. And ये तो आपको पता ही है O minus, O minus, O minus. You know that already, right? So when two oxygens form a ring or an infinite chain, both are possible. Ring and chain, both are possible. So the unit, the repeating unit is going to be this. When I have a ring, the overall is going to be SiO3 whole n 2n minus. That means if I have a three-membered ring, let's write it over here. If I have a three-membered ring, that is, I'm repeating the same unit three times. तो चलो देखते हैं. SiO3n 2n minus. Just remember this common formula for ring silicates. Why? Because I'm putting n is equals to 3 for a three-membered ring. Then it becomes SiO3 whole 3. 2 into 3 is 6 minus. So overall formula is Si3O9 6 minus. Look over here, isn't it? This is a three-membered ring. Now, if I just do the same thing, I put the n value 4 over here. It becomes Si4O12. 4 into 2 is 8 minus. See, this is what I get. If I put n value is equals to 6, because now I want a 6-membered ring, that will become n value is equals to 6 will become Si6 O. 6 into 3 is 18. 2 into 6 is 12 minus, this is what I get. So this is exactly what I have for a big 6-membered ring right over here. Okay, so just remember this little formula I've given you for ring silicates. These are ring silicates. Okay, now these are the example: bentonite, barium TiSiO3 whole 3. So this is a 3-membered ring. Okay, because the silicates are having 3 members. Has 3 rings. And beryl. Beryl is the only ore of beryllium which is extracted as a ore, right, commercially. So beryl, you have to remember, is again a ring silicate, has 6 silica rings. So this one is the structure of beryl, and this one, the smaller one, is the structure of bentonite. Okay, just one page you remember, guys, nothing more, just one page. Now, single chain silica are called pyroxenes. Single chain. This is a single chain. This is known as pyroxene. Okay. Synthetic metasilicates Na2SiO3 have simple chain silicates like this. Okay. Double chain silicates are known as amphiboles. You see, these are, let me write over here. यहाँ पे लिखने का जगह नहीं है, so I have not written, but let me write the formula closer to this so you remember. The pyroxenes are Si2O5 N minus, I guess. This is 2 minus whole N, right? This is going to be the repeating unit. I should write the 2 minus inside because that is going to be the repeating unit of the single chain silicate. Okay, let's write the single chain silicate pyroxene properly. Whole N. Okay, when you are having double chain silicates like this one, they are going to be amphiboles. They are going to have this formula, this one. These are amphiboles. Okay, और इसके example क्या है? Tremolite, calcium magnesium silicate, which is having this formula. Next, sheet silicates, which are actually just like sheet, just like graphite, you have different sheets on the top of each other. Those are known as phyllosilicates. Phyllo means leaf-like and are easy to cleave just like graphite. Okay, so just remember, sheet silicate like graphite are known as phyllosilicate. Now, talc is a typical sheet silicate which is having this formula. Again, this is the formula of a sheet silicate. So you see, the formula of a sheet silicate and a single layer pyroxene silicate is the same. Okay guys, if you can just make a table in your notebook: orthosilicate, pyrosilicate, ring silicate, ring में भी दो आते हैं, then sheet silicate, all of these, make a table. Okay, how are you going to make a table? The name, the formula, the examples. Name, formula, examples. Just make a table and remember the table. Okay, because many a times they have been asked directly. All right, very simple. Chalo. Next important one. Now, previously I asked you a question based on the sodalite cavity in a zeolite. What is the shape? It is a truncated octahedron. So you see, what is a truncated octahedron? Right, truncated means octahedron को हमने cut कर दिया. We are just cutting an octahedron like this, and that becomes a truncated octahedron. Now you can just take this over here and fit it inside this. Okay, so what is a zeolite? Let's talk about what is a zeolite. What are the different applications of a zeolite? Okay, you have already got some idea. Let's expand the idea. So zeolite is a group of several microporous having small cavities, crystalline aluminosilicate mineral, commonly used as commercial adsorbent and catalyst. Adsorbent कहाँ पे use होता है? Catalyst कहाँ use होता है? We'll talk about it. So zeolites are what? These are just aluminosilicate minerals having this particular shape, sponge-like shape. Sometimes they are compared to sponge-like shape, and sometimes they are mentioned as having honeycomb structure. These are just common ways of calling it. This is how the structure is going to be, having a truncated octahedron cavity. Chalo. So zeolites are used for shape selective heterogeneous catalysis. One important use. What is heterogeneous catalysis? Let's say I am having some anion, some big anion, which will not go into water because zeolites are going to be soluble. A minus can set into this cavity and K plus is going to be free. So heterogeneous catalysis means I have two layers, one organic, another aqueous. Aqueous, organic, like this. So I want my zeolite to behave as a phase transfer catalyst. So exactly it is going to be. It can help you in phase transfer catalysis and shape selective catalysis. That means only a part of that molecule will fit into the cavity which is having a proper cavity, the same size as the cavity. Okay. For example, the molecular sieve ZSM5 is used to synthesize 1,2-dimethylbenzene, that is xylene, our orthoxylene, for use as an octane booster in gasoline. This is a very important application. Particularly ZSM5 is used for the xylene production. Just remember this. Okay. Another example, another use is used as ion exchange, water softeners in detergents. So these zeolites are used as water softeners because they can, based on the different types of zeolite, they can absorb or they can fix the metal ions like calcium, magnesium, sodium based on their cavity size, then helping the water to soften. Now, absorption of molecules, selective gas separation, gas chromatography, all of these are very important uses of zeolite. Solid acid, cracking high molar mass hydrocarbons or for fuel and petrochemical intermediates. So this is where the ZSM5 is used. Okay. Shape selective alkylation and isomerization of aromatic for petroleum and polymer intermediates. Right. तो ये वही चीज है जो हमने orthoxylene prepare किया. So three most important applications of zeolite you know the structure and you know the cavity, truncated octahedron. Okay. Chalo, let's move onwards and now we are going to talk about silicones. Silicones. What are silicones? They have been asked mostly in every paper, every year, mostly one paper or the other. Silicones are just polymers. Okay, synthetic polymers having both the silicon, oxygen, and some alkyl group. Okay, now silicone polymers, more properly called as polysiloxanes, do not have carbon as a part of the backbone structure. मतलब backbone में नहीं है, it could be present in the substituent but not in the backbone. Okay, although silicon is in the same group as carbon in the periodic table, it has quite different chemistry. Silicones, particularly these silicones, they are water repellent, heat stable, very resistant to chemical attack. So these are mostly stable, very, very stable. And they are used in various industries, oils industry, greases, rubber like material. So they can be used for binding, for insulating, many different things. Other silicones are used in hydraulic fluids, electrical insulators, moisture proofing agents in fabric. So guys, why am I telling you the uses? Because usually you just study the reaction of formation of silicone and how they are reacting further. So uses are also important, isn't it? So let's just discuss some of the uses, some of the reactions. So for example, if you are having a molecule like this, you have a Grignard reagent reacting with silicon tetrachloride. Okay, one reagent you have given, that means RSiCl3 is going to form along with MgCl2. This is just one reaction. Now, if for example you go on giving Grignard to this product which is formed, then what will happen? RMgCl plus again SiCl3. Again, it is going to react. You will get R2SiCl2 plus MgCl2 once again. Okay. Again, do the same thing. R2SiCl2 plus RMgX or MgCl. That again gives you R3SiCl plus MgCl2. Again, R3SiCl plus again Grignard. One more last replacement. That is going to give you R4Si plus R plus MgCl2. So what did you find out basically? That we can do one by one replacement of the alkyl group on silicon if there are replaceable groups present like halides. Very easy replacement. Now, what are the important molecules? This, and this. These three are very important for formation of silicones, but this is not because it is all alkyl now. It is unreactive. It is unreactive, so no need of that one. We are just going to take these three and react them with water. चलो मान लिया इसको water से react किया. We are reacting this with water. What will happen? It is going to give you hydrolysis and give you 3 OH groups. Again, react this with water. R2SiOH whole 2. Again, water. R3SiOH. Just one single group. Okay. Now further, if you want to heat it, you are heating all of them at a certain temperature. What will you get? Let's see in the other slide. So you started with RSiOH whole 3. You are heating this system. What will happen? Elimination of water will happen, and along with that you are going to get, see, there were actually OH present like this. Okay. Now what happens? One more such molecule comes. And it is going to eliminate a water molecule together. And after that what happens? You have eliminated H2O. One H2O from over here. I have to rewrite this one. And it forms a dimer like this. It forms a dimer like this. Okay, no problem, easy. So the same thing can happen with this OH, this and this. That means I can do a branching everywhere I see an oxygen. Let's write the R over here. Let's write the oxygen in middle, and I can do a branching in this way, onwards and onwards, and one more like this, so on and so forth. What has this become? This has become a silicone. Silicones are complete polymers. The chain is going to go on and on and on until it finishes. So this is what happens when I'm taking RSiOH whole 3 and heating it. Similarly, if I'm taking R2SiOH whole 2 and then if I'm heating it, what happens? Two of the sides I'm having alkyl group, only two other sides I'm having oxygen. So I'll just do the dimerization over here. Yes, one more silicon, one R, another R. So this is not going to be like a very big polymer. It has to end because only two ways are possible, no? So that's why either it is going to end like this or the chain is going to go for a while and then stop. What about if I'm taking R3SiOH, only one OH group, and heating it, minus H2O? What is that going to give you? Three side alkyl groups are present. That means only a dimer is possible. Only a dimer is possible, nothing more than this. Okay. So there has been a question in your CSIR NET exam based on the silicon only, that if I want to make a silicone polymer, what is the starting material I will take? What is the ending material I will take? That means if I want to start the branching, this is the best for branching, and this is the best for chain termination, because if you put 3 alkyl group, it is going to just form one bond and terminate the chain. Okay. Alright guys, so now we are going to do some questions based on group 14. So you see, this question is taken from June 2024. The correct order of covalency in the XF bond among the following species is. So yes, try this question by yourself, nothing too difficult. Correct order of covalency is asked, right? Yeah, let's see. What does the covalency depend on? Either the size of the central atom, or the oxidation state of the central atom, or the oxidation state of the central atom. That means if I am talking about group 14 to group 14, 15, 16, 17. Group 14 से group 17, the size is definitely decreasing. But here the last one is IF7. This is going down the groups, so the size is increasing. So I don't think that size is the only factor over here. There are two factors. What are those? The oxidation state. Silicon bigger in size, +4. Phosphorus smaller. This is +5. Sulfur again smaller in size, +6. About iodine, +7. So maximum, iodine has maximum oxidation state over here, so it might be pulling the electron pair closer to itself. And what is the anion? The anion is fluorine. So whatever is your central atom, let's say A, I'm writing for atom, so that wants to pull the electron pair towards itself, and fluorine being electronegative will pull it towards itself as well. That means maximum covalency for IF7. So what is the correct order? Maximum for this, then this, then this, and then this. First one is the correct answer, both on the size and majorly on the oxidation state. Majorly this factor. Very easy. Next one. Among SiCl4, PoCl3, NF3 trans of this compound, those with zero dipole moment are. Now this is a question of chemical bonding. Just try this out. Zero dipole moment you have to find out. Do this by yourself, okay? Very simple. Alright, so these are the structures of these four molecules. Which one is having zero dipole moment? Definitely this one, because it is trans. Then SiCl4, because it is tetrahedral. Because of the perfect geometry, the dipole moment is cancelled out. And here also, because the trans, all the similar groups are trans, that's why dipole moment is zero. For PoCl3, there is going to be some dipole moment, and for NF3 again some dipole moment. So with zero dipole moment are SiCl4 and trans compound. C is the correct answer. I hope you got it correct. Next, 2022 examination, February. Choose the correct statements from the following. The trend in Lewis acidity among silicon halides. Tin 2 chloride can act as a Lewis acid and not as a Lewis base. Aluminosilicates can display Bronsted acidity. So everything about group 13 and 14. Mostly 14. Chalo, do this. I teach these two examples together always so that you know the contrast. The trend in Lewis acidity among the silicon halides. So we are discussing the silicon halides and then we are discussing boron halides. Why? Because boron halides, they can do pi back bonding. They can do pi back bonding, and here BF3 has maximum 2 pi back bonding. So BF3 becomes least acidic. And iodine does not show pi back bonding because of large size. That's why it shows poor pi back bonding, and this is the most acidic, right? So here I am going to write, this is the Lewis acidity order. This is the Lewis acidity order of boron halides. Okay. Now we go to silicon. Silicon does not show pi bonding. The only factor that affects acidity is electronegativity of the halide. So this is the correct order. One is correct. Only based on electronegativity only based on electronegativity of X halides. So just always remember these two together because of comparison. Now tin 2 chloride SnCl2 can act as a Lewis acid and not as a Lewis base. This is wrong because tin is amphoteric. Also it is amphoteric for one more reason, because it can disproportionate both to tin 0 and SnCl4. So that's why it can go both lower and higher oxidation state. It can react both with acid and base. This is wrong. Aluminosilicates can display Bronsted acidity. Now what is Bronsted acidity? H plus. Bronsted acidity talks about a proton. So aluminosilicates can break down water and take away the OH minus and give H plus. So this is also correct. 2 is correct, 1 and 3. 1 and 3 are both correct options, so 2 is the correct one. Right, and last, consider the following statements. PbCl2 has low solubility in water. Sulfides of arsenic 3 and antimony 3 are soluble in ammonium sulfide. This one, whole 2s. SNS is soluble in yellow ammonium sulfide, whole twice s. MNS is precipitated by passing hydrogen H2S through acidic MnCl2. So which of these is correct? Right, tricky question this one, because all of these mostly are asking reactions. Yes, correct statement you have to find out. PbCl2 has low solubility in water because lead is a heavy metal, and this is true. It has a low solubility product. The Ksp value is low. That's why this is correct. Low solubility in water. Sulfide of arsenic and antimony are soluble in ammonium sulfide. Why will it not be? Because ammonium sulfide, when it is ammonium sulfide as a solvent, then definitely the arsenic 3 plus and ammonium 3 plus are going to be more soluble, right? Because the solvent is only sulfide, right? So this is also true. SNS is soluble in yellow ammonium sulfide. Again, the sulfide is going to be soluble in sulfide. Yes, it is. So these three are correct. Manganese sulfide is precipitated by passing H through S to MnCl2. Now, I think when this happens, MnS, this is the less reactive MnS. Theoretically it looks fine, but HCl being a strong acid can react with this further and give you back the more soluble compound. Yes, so I think that D is going to be incorrect. A, B and C are the only correct ones. Alright, so look out more main group element questions in the previous years. You will find out plenty and plenty of questions on main group, and that's what is making this topic important. So I will see you all in another video discussing group 15 in the next one. Alright, have a nice day. Bye everyone.